It's a common saying to say, you've got to draw the line somewhere, and in our lecture today on regression, you'll learn exactly where to draw that line. In today's lecture, we'll discuss the basic assumptions and qualities of regression. We'll then move into discussing the regression method and the process for looking at a regression model. We'll also touch on topics from the later chapters on regression, 11 and 12, and discuss looking at the regression line and error in regression. Finally, we're going to look at some interesting research that uses a simple regression model that will be a nice model for you to consider when you're looking at when you're thinking about research in the future, or I know many of you are going on to do a class in research methods after this course where you have to design a study. When you design that study, all this information about modeling is going to be really valuable. So we'll read through some research I really like, the power posing research. You've heard me discuss it. We'll revisit it again later in the class, but we'll also go over some research scenario problems and correlation that are not from your book, but that give you some insight and practice into reading problems about correlation or regression and how to tell what technique to use. Now, we only have a couple techniques so far, and they're quite related, so it's a pretty small difference at this point, but we're going to start practicing this skill more and more because as we move through the next several chapters and exams, we'll focus increasingly on being able to correctly choose the right statistical procedures for a given research scenario, and then how to report results from said scenarios. Finally, we'll go over the research scenarios we're going to look at today. We'll briefly go over how to use Excel to get correlation and regression information. The goal of research generally is to explain why variables vary. We design experiments to help us better understand what factors can help to predict outcome variables of interest and explain variance in those variables. It's possible to quantify the relative importance of any variable, and regression is a very helpful tool in doing that. We'll primarily cover, at this stage at least, regression on 2 interval level variables, but it is possible to do regression with variables that are measured at the nominal level, or a nominal predictor and an interval outcome. And that's called logistic regression, but we're not going to go over the procedures for that. It's enough that you're aware that it exists as a possibility. Regression enables us to describe how one variable depends on another. Thus, the regression line for y, so if the regression line is for the outcome variable, or the regression line for y on x, estimates the average value of y, the outcome variable, for each corresponding value of the predictor. And we see associated with each increase of 1 standard deviation in the predictor, there's an increase of only r being our correlation coefficient, of only r standard deviations in y on the average. And we'll unpack that idea a little more later on. Finally, The regression method uses the correlation coefficient to estimate the average value of y for each value of x. In this scatter plot, you can see the height and weight for one of the 401. So you can see the height and weight for each of the 471 men in the 18 and Haynes 5 in the 18 to 24 age range. And we've seen this graph before throughout our chapters on correlation, now regression. And let's just talk about a couple of key aspects of this diagram. The vertical strip, that is these two dashed lines, that represents men who are about 1 standard deviation above average in height. Why are the lines here? Because they are choosing to highlight 1 standard deviation above average in height. Those participants who are also 1 standard deviation above average in weight are plotted along the dashed SD line. And you can see that right here. And then here's our dashed line. And our solid line is our regression line. This is a standard presentation for a regression scatter plot. There's the scatter plot, the regression line, the standard deviation line. The regression line would be generally solid, the standard deviation line generally dashed. And again, the vertical strip, the dashed lines, this is a standard notation. So when you see these in other future research articles, you'll know how to read them. And so if we look along the regression line, we can see that it estimates the average weight for each height. It's obviously not the actual weight at each height of our participants. It's the predicted weights based on the heights that are part of our range. And predicting an outcome based on a predictor variable, this is a very common application of regression, essentially the primary reason to use regression. Before we break down the regression method, let's just take a final look at the requirements for regression. These are also called underlying assumptions of the test. And one is that the variables are at the interval level. We've discussed that already. And this is just for our class procedures. As I mentioned, there are regression procedures available for other variable combinations, but we're not going to do much treatment of that in this class. Suffice it to say, you could certainly do it in a statistical analysis program. Another really essential assumption here, and just that's very similar, the assumptions are actually the same for regression and correlation. The interval level, the straight line relationship. The samples must be chosen at random. When samples aren't chosen at random, there are still statistical tests available that we'll get to, but they're not as powerful as tests that have random selection as a requirement, and random selection is really essential. Finally, normality for both the variables, as in both the variables must be normally distributed. When trying to understand the regression method, it's important to remember that we're looking at the increase that associated with each increase of 1 standard deviation in the predictor. There's an increase of only r standard deviations in the outcome. And it's easy to get into, so you have two different standard deviations. You have the standard deviation of x, which helps us assess changes in x and variability in x. The standard deviation of y helps us assess the changes in variability in y. And on average, y goes up by r standard deviations. It's easy to get caught up in a rhythm thinking that if x goes up by one standard deviation, so does y, but that's not true. It could be true for some individual variables, but on the whole, we see that the correlation coefficient is a nice indicator of the amount that y would go up for each 1 unit of s, or 1 standard deviation of x. So let's take a look at this. And here you can see this illustrated on abbreviated version of a regression diagram. And so we're starting at the point of averages, going over by 1 standard deviation in x. You're going to go up by r standard deviations of y. How many is r standard deviations of y? It's whatever r is. It could be 0.6, it could be negative 3.1, it could be any number between -1 and +1. And finally, we get that regression estimate. Now, this point, that is the regression estimate, it's important to remember that this is a predicted outcome value, not an actual outcome value. And we can look at the amount that our actual values differ from the predicted values. That's an important measure, actually, but it's just a little teaser for the future. Let's think about why R is the right factor. Well, it's important to consider 3 examples, and it's often helpful in mathematics and statistics to take a couple of extreme examples, which is what we do here, and look at how the association or the test deals with the extremes, because it can give us insight into where there might be problems, or why it makes sense. So if r is 0, there's no association between our predictor and our outcome. A 1 standard deviation increase in x is accompanied by a 0 standard deviation change in y. There just is no association. When r is 1, or a perfect correlation, all the points lie on the standard deviation line. So literally the points themselves would form the standard deviation line, and a 1 standard deviation increase in x is accompanied by a 1 standard deviation increase in y. Why is there a 1-to-1 association here? Because our value of r is 1. Now, when we have a -1, there's a perfect association still between x and y, but in this case, the line slopes down. So all the points again lie on the SD line, but instead of an increase in x is going to be accompanied, let's see, this should say a decrease in here. So a 1 standard deviation increase in x is accompanied by a 1 standard deviation decrease in y. Sorry about that. Again, with the in-between values of r, we would need a more complicated mathematical argument to prove it, but r is still the right factor. If r works for all the extremes, in the absence of the mathematics, you'll have to believe me, it works in the middle too. So we encounter the graph of averages, and the graph of averages is a smooth version, or the regression line is a smooth version of the graph of averages. Thus, if the graph of averages follows along on a straight line, the line is the regression line itself. In some situations, the regression line smooths away too much. And this can be problematic. It's a common problem to encounter if the regression can be what's called overfitted. And we'll unpack that idea of overfitting when we look a little more at third variables, because when we which we will, not just third variables, but additional predictors. So in our lecture on chapter 8, we discussed how we're currently looking at just one predictor and one outcome situation, but it's very, very common to have a situation where there's two predictors and one outcome. There's always only one outcome. And you could have multiple predictors, and essentially the line is especially vulnerable to being overfit when there's many predictors that are put into the model, because there just can be too many. It's best to have as simple a model as possible. What's a model look like? Don't worry, we're getting there. Finally, when you've got nonlinearity in your graph of averages, again, you're unable to use the correlation or regression, and so, or nonlinearity, excuse me, in your regression line. You can't use the correlation, which is essential in regression. So it's best to use the graph of averages when you're faced with a nonlinearity scenario. Let's take a quick look at this problem. The figure below, which is on the next page, but it's also in your text. Sorry, I navigated away for a moment. So it's in your page 163. And you can see that the figure is based on a representative sample of married couples in New York, and the graph shows an average income of the wives given their husband's income. With 102 couples, the husband's income was in the range of $1,000 to $5,000. For those couples, the wife's income averaged from $15,390, as indicated by the point 2,500, comma 1,500, 390. With 58 couples, the husband's income was in the range of 5,000 to 10,000. Data are probably pretty old, huh? For those couples, the wife's income averaged 18,000, as indicated by the point, and so forth. And the regression line is plotted here in the graph. You can see this. Oh, they were just showing us the bottom of the diagram. True or false, there's a positive association between husband's income and wife's income. Well, this is clearly true. We can see that there's a clear positive association here. The line is going, showing an increase in Y per unit increase in X. And how would we explain this? Well, using a social reasoning. So people of higher incomes or from a more privileged background tend to marry people who are also from a more privileged background or who have a higher income. This is true all along the scale. So people with a lower income are more likely to marry another person who's also from a lower income or from a lower income background. And we're going to look specifically here at the dot at 127,500. Why is it so far below the regression line? Well, we've got here an outlier, a unique situation. So maybe we have a husband who is from who has a very lucrative job, and a wife who maybe only works part-time. So there's a logic here to explain why that dot is so far below. But finally, if we use the regression line to estimate the wife's income from the husband's income, would your estimates generally be a little too high, a little too low, or just about right? Specifically for the couples in the sample with the husband's income at the range 65,000 to 80,000. So the question here is asking, essentially, if we switched the position of the variables. So instead, we had wife on the x-axis and the husband as the outcome variable, the husband's income. Would we expect the estimates to change much? So not likely. We're not likely to see a dramatic change there. Just like the correlation, it doesn't, when you've got two variables, it doesn't matter as much if you switch them around. Oh my God, I'm sorry. So regression helps us get a graphical representation of the data. In fact, all of the topics we've discussed in this unit include the graphical representation in various layers. Scatter plot, the regression line, the standard deviation line. And regression has a lot of similarities with correlation. Correlation's essential to doing regression, and both give us the strength of the association, but regression specifies the nature of the relationship. So the calculations are the same, but it has to do with the way that the relationship is specified and the conclusions that can be made. So when we fit a regression line through a scatter points, the coefficient, the correlation coefficient, measures the degree of fit of the points to the line. In interpreting the regression line, we think about the following values. You've got the y-intercept, A, and this is the predicted value of y when x is 0. We discussed this already a bit in our chapter 7 lecture. And the y-intercept may or may not be meaningful. It depends on your data. Sometimes the intercept is valuable, like if it's possible that x could take on a value of 0, then the y-intercept is more likely to be valuable. But if you instead have a research situation where x, the predictor variable, couldn't possibly be 0, then the intercept is not especially helpful generally or meaningful. When is a predictor variable not possible? When is it not possible for our predictor to be 0? Well, we've already seen some examples of that in examples that we've looked at today. So height and weight. It's not possible that someone's height could be 0. There's always a minimum height of something. So, the intercept for that graph of height and weight that we looked at earlier, it's not likely to be useful. The regression coefficient, B, or as we discussed, otherwise the could be indicated by M as well. Regression could be B or M. Both would be the same. It's just a matter of convention. Different researchers might use different ways of referring to these. But the regression coefficient gives, oh, no, sorry. Oops. Actually, the regression coefficient is always B. The slope is M. My apologies. The heat is getting to my mind. Hopefully I don't commit a homicide too. Just kidding. So the regression is, the regression coefficient gives us the change in y for each increase in x. This sounds familiar, why? Because it's the same as the correlation as y goes, but why would we need regression if we have correlation? Because remember, there are situations where we have more than one predictor, and you can't actually, you can do correlation with several variables, but you're always looking at the correlation between two of those variables. You can't put them all together in one model, but regression makes it possible to look at multiple predictors. And that's what we're going to do right now. Before we look at the results section that is going to illustrate some of these more advanced concepts of regression, let's talk about what is power posing, because the research we're looking at is on power posing. And power posing is when you stand like a superhero, or essentially it involves adopting some kind of expansive stance. So there's the classic Wonder Woman stance, or the Superman, which are similar. Also, you might put your hands up, any type of expansive stance. And in the power posing research, they use other expansive stances that are, there's some seated expansive stances. There's a variety of different power poses. And this is actually, the research is linked. I believe there's a folder already in your lab area with some of the power posing research. If not, it'll be there by tomorrow, because we have discussed this more through the class. Both this first research, we'll look at the whole canon of the power posing research, because some researchers saw this. They thought that, well, could standing like Superman for 2 minutes have an effect on later performance? Specifically, they looked at in a job interview, which is what we're going to look at their job interview research today. And they tested the saliva of people who power posed for 2 minutes before the interview, and people who were, and again, this is an experiment, so subjects were randomly assigned to a power pose for just 2 minutes before their interview, or to adopt a low power pose. This is one where you're hunched over, you're not expansive, but contracted. And they tested the saliva of the power posers, and generally they found that power posing was associated with increases in certain hormones, in particular testosterone, which is helpful because it is generally associated with increased confidence and risk-taking. Why is that helpful? Well, I mean helpful in the context of, I am going to advocate that you integrate power posing into your statistics study regimen, because power posing can help you to increase your confidence, reduce some stress hormones, cortisol, which I'm sure you'll all agree that a reduction of stress when studying statistics would certainly be helpful. How could risk-taking be helpful? Well, because as I keep saying, you got to take a risk and make some guesses, because you're not always going to be right. That's part of the risk. is to just practice it and just try it. Take the risk, open the book. And so this is just a general overview of power posing. And let's, I've skipped a little bit ahead to the results section of this study. And the study itself, like I said, should be on Blackboard now, or I'll check that it's there tonight so you can look at it. It's helpful, very interesting. I usually assign reading the article before doing this, going over these results. I just forgot. So my apologies there, but I've given you a general overview. They have these two groups of participants, the high power posers and the low power posers. We measure their hormone profiles before and after power posing, and we also measure their performance in the interview and specifically look at some associated variables that we expect to be confounders. Now, let's step back a minute, and we're going to just unpack a little bit how to read through a results section and start to make sense of it. Now, not all of the things in here are going to make sense fully to you yet, but their regression model is simple and nice, easy to interpret here. So we'll take a look at that. But first off, you can see that they provided this manipulation check. What's a manipulation check? Well, that's when they're just saying, we want to make sure that there was an effect of our treatment. So did power posing have an effect on overall feelings of powerfulness? And as expected, the high power posers felt significantly more powerful than low power posers. Now, let me highlight some specific aspects of this sentence for you, because we will be thinking more and more about how to correctly write sentences about statistical tests. This is an article, provides some really nice examples that are easy to interpret of effective ways to write these sentences. So specifically, what I'm talking about here in the first blue box, you can see that both groups are identified. High power posers, those are our first group, felt significantly more powerful. So we've got the group and the dependent variable. And then you see here in parentheses, there's the group mean. This is a standard procedure to report at minimum a group mean, along with oftentimes along with a standard deviation in a result sentence like this. And when we do that, so this is standard. And when we do that, when we report the mean and standard deviation, they are put in parentheses as they are in this example. Why am I emphasizing this so much? Because I know what your final exam looks like. So you should, you will be writing up some results sentences for different tests on the final. And one of the things I'll be looking for is that you presented the statistics appropriately. You presented the statistics that make sense. So one part of making them appropriate is to do them like this. So a sentence you should be able to read a sentence and have it make sense without a parentheses. That's just a general rule of grammar. If the parentheses always contains additional information that is sort of background information, but is not essential to the grammatical structure of the sentence. I hope you can see that here. If you're not quite seeing what I'm talking about, or it's sort of making sense, don't worry. We're going to look at this. We're going to get more practice with this, but I'm trying to unpack this with this nice example for you to help ease you into the pool of sentence writing. So I've looked at the first part. We have group one and their effect or their performance on the dependent variable, along with a summary statistic in parentheses. Then finally, the second group. And you can see that this over here, more powerful than the lower power posers. These are our second group, and their mean is in here. It's also notable that they described this sentence by stating the direction of the relationship. They didn't just say power posing has an effect on feelings of power. That's insufficient because we only have two groups. So we know that if there is a significant effect, that we can already tell just by looking at these group means which group is higher and lower. The fact that this is significant tells us that the one group is higher than the other. Now, I know we haven't discussed statistical significance or determining statistical significance, at least in depth yet, but we will. And it's just a matter of doing tests. We actually can do it for correlation, and you just look up the probability of the score that you obtained, but we're going to have to cover probability a bit first. So one other feature of this sentence I want to draw your attention to, and that is this value, these numbers here at the end. So we've got this clear sentence with a comma. So the relationship is stated, comma. This is another key point here. Relationship stated, comma. Then there's statistics afterwards. Now, we haven't talked about the F statistic yet, so don't let that scare you. We will discuss it briefly, but the big thing to remember is that you would provide any additional information about statistical tests after the comma. So in this case, the specific information that is always required would be the test that's done. So in this case, they did an F test with 1 degree of freedom. I know we haven't talked about that. The degree of freedom is in the parentheses. But this could easily, if this was a correlation sentence, have an R here, and then this would be an R value instead of an F value. Various statistical tests have letters or symbols associated with them. And so this is a common presentation here, and you should go back to this. This is a great example. There's a p-value. This is the p-value here, which we'll discuss again in our forthcoming discussion on probability, but I just am previewing for you that this is a great sentence. And they further tested the overall performance and hireability. To just give you a little preview of what an analysis of variance does, is it's essentially a test where you can use, you've got a nominal independent variable and interval level outcome variable that's normally distributed. And it tells you if there's a difference between your groups. That's an extremely brief summary of an analysis of variance or ANOVA test. And so it's used to examine the effect of power poses. And they looked here at performance, like performance in the interview, and hireability as rated by the interviewers. And this was an experimental situation, so it was technically a pretend interview. And they found that the coders, these are the people coding hireability and coding performance, rated the higher power posers higher on performance. We see the same pattern in our sentence. They're saying high power posers are significantly higher on this outcome on performance with a mean than the low power posers with their mean. So we've got a similar format here. And they also found that high power posers were significantly higher on hireability than lower power posers. And so you can see the trend in the sentences here. And this should already help to give you some insight into reading research articles. This is an entirely standard presentation of the data. And remember, if you're reading an article, just because there's maybe a statistic you haven't seen before, it's no reason to stop reading the results. There's already a lot of things in a standard research article. This is really famous research, actually, that you can definitely understand, namely our next session. Oh, they did one more ANOVA. And just in case you're wondering, did power posing make people more likely to adopt an expansive stance during the interview? And then that problem maybe had an effect on their performance or hireability. They didn't find that. So, but it would be a confounder potentially. It's a body expansiveness is a potential confounder. So when we're doing research, we have to identify a possible potential confounder like this and assess it in a systematic way, and then look to see if it is actually affecting our outcomes. And so you can see they did that. They coded the videos on a 7-point scale, etc. They did another ANOVA, and they found there was no difference in terms of their body expansiveness during the interview. And this is another great example of a no difference statement. So they revealed no difference between high and low power posers on the body expansiveness, our dependent variable. So we see no difference in our, again, both groups are identified, both groups in our independent variable, their means are provided, and the dependent variable is detailed. And always the statistics afterwards. Finally, the regression analysis. Now, why go through all that other stuff ahead of time? Well, because that's the groundwork to understanding why they have these particular variables in their regression. So you can see that they wanted to understand why high power posers experienced better job interview outcomes on the critical dependent variables. They have 2 dependent variables, but each dependent variable is modeled separately. So a model can only have one outcome. And they regressed the mediators onto the dependent variables. This is just common language for saying they looked at the variables in a regression model. And they found that presentation quality predicted performance and hireability. And speech quality didn't predict performance or predicted neither performance nor hireability. So it really didn't matter how well the people spoke during their interview. That had no effect on their hireability or performance. It was really down to the presentation quality, and that's what they're seeing, suggesting that power posing is going to have a good effect on. And you can see this here. Here is the model. So we see presentation quality predicted performance. This B is a beta, is what it's called, but it's the regression coefficient, aka the regression coefficient identified in our treatment of regression. These other values, the t-test, we'll get to that. But here you can see that the regression coefficient is pretty high when we look at presentation quality. Here we have presentation quality and its prediction of performance. So these are our actual variables. They're laid out in this model. This is a conceptual model, the squares themselves and the arrows between them. And the numbers that describe each direction help to give us an idea of the strength of the relationship. So power posing has, and it's the correlation. So the correlation between power posing and presentation quality was pretty modest. But the association between presentation quality and overall performance is extremely high. And so we could say that, so this gives us a nuanced detail of understanding the whole variable relationship. So we started out just using power posing to predict overall performance. But that they knew that wasn't enough. There's another variable in there. And they found that when they looked at presentation quality, that accounted for this relationship. That the effect of power posing works through presentation quality. You see that? We call that mediating the effect. So when let's step away from this for a moment, and I'm going to show you. we can, as I mentioned earlier in our lecture, we can use this to literally write out the model mathematically, like we did when we had our basic line equation. And when we do that, our basic equation for a line is y equals mx plus a. Remember, a is the intercept, the slope, the x variable. When we turn this into regression, we've still got our outcome. And we say it's equal to, we'll reverse this. So we'll remember to put the intercept in here first. Remember, it doesn't matter what order the terms go in mathematically. So we've got our intercept in there. It's always in there, but we also need to consider our x variable. Our first one is going to be, I'll put it in parentheses, the x. This is x1 pose. You know, the pose adopted, the x variable, and it's got a slope or a correlation. And then we add in a second one that is going to be presentation quality. That's another predictor. It's also got a slope. And this is the mathematical representation of the model that they've outlined here. Somewhat simplified mathematical representation. I did leave out the error term because we haven't discussed that yet. So they've got a second model here, but we will save this for our next discussion of regression. Why are we discussing regression and correlation in so much depth? Because they are so important right now and they get so much emphasis in social and health research. You know, almost any research you pick nowadays has correlation or regression in it. So, or excuse me, correlation and regression, but especially regression is so popular. So it's important to really get a good understanding of it. And I can tell you from experience that the professors who required you to take this class, you know, in your home departments, they really like you to get a good understanding of regression from this course. So it's a priority topic. And to be able to understand it in a research format like we're doing. Now let's take a brief break and we will discuss how to go over these problems and do them in Excel. Next, we'll